Okay, let's finish this Asela-Scully theorem. Remember that we are going to prove that if you have a sequence fk, it is a Cauchy sequence, right? Okay, so last time we already mentioned that it's equivalent to say for any compact set and any epsilon, you can find a capital J so that k j greater than capital J, this supremum is less than epsilon. So that's what we have. Now let's assume K is compact, this compact set. Okay, so for a compact set, it's totally, K is totally in G. G is open, remember. So K intersect the boundary of G empty. Okay, so this is an empty set. We know that boundary of G is closed, compact set is also closed, but if you have two closed sets, the distance may not be positive. But once one set is compact, so it's like this. It's from topology. If A, B are closed, and A is compact, and A intersect B empty, then the distance between A and B, the distance between two sets is the infimum of the distance A and B, here A in A and B in B. This is definition of distance. The distance between A and B is going to be strictly positive. But, okay, so this is the result. But if only AB closed, A intersect B empty, we have the distance between A and B, we can only have greater than or equal to 0. It could be 0. The distance could be 0 because we are talking about the infimum. The simplest case is like the infinite curve at asymptotes. Okay? So for example, you have this curve. This curve y equal to 1 over x. This one branch is closed, and the x-axis is closed. And these two curves have empty intersection, but the distance, the infimum is 0. Okay, because none of them is compact. If you have a compact set, then it's going to be strictly positive. Okay, if you are interested, you can try to prove it. Okay, so here K is compact. Boundary of F is closed. So the distance between K and the boundary of G is strictly positive. Strictly positive, let's call it R, a positive number R. Okay. Then we make this compact set slightly bigger. So let K1 be the set of Z so that the distance between Z and the K is less than or equal to 1/2 of R. So you make it slightly bigger. And then we see that the K1 is also compact. It's closed and bounded. It's also compact. And K is inside the interior part of a K1 inside K1 inside G. All right. Okay, so now we have this F. The family F is equicontinuous. At each point of G. Then F is equicontinuous over the compact set K1. Okay, over the compact set K1. It means it's equicontinuous. So choose delta such that delta is less than 0.5 of r. Okay, with delta such that delta has and the distance between f of z prime is less than epsilon over 3 for all f in the family f. And whenever z and z prime are in K1. So that's the definition of equicontinuous over a set. Sure. With the distance between z and z prime is less than delta. Okay. Okay, so now remember we have this sequence Zn. So let D be the intersection of Zn with this K1. Okay, D be the intersection of Zn with K1. So if this arbitrary Z in K, for every Z in K, remember this is a dense set. There is a Z sub n with the distance between Z and Zn less than delta. All right, and delta is less than 1/2 r. Delta is less than 1/2 r. So it means the distance between Zn and the K, remember Z is inside the K, Z and Zn is less than delta, so Zn, the distance between Zn and K is less than 1/2 of r. It's less than 1/2 r. What is K1? This is K1. So this implies Zn belong to K1. Okay, Zn belong to K1, Zn is inside D. Zn is inside D. Okay, so what we got? Every Z, there is a Zn, so that Z is covered by the ball centered at Zn with radius W. Zn is inside D. So the ball centered at Zn with radius delta, Zn inside D is an open cover of K. It becomes open cover of K, right? K is compact. K is compact. So there's a finite subcover. Finite subcover K is contained in the union of I from 1 to n, B of Wi with radius delta. Okay, so now we have finitely many stuff. Okay, and we know that the limit of fkwi, k approaching infinity, this limit exists for I from 1 to n. All these exist. We already showed it exists. It exists, then you can find, there are only finite many, so we can find a uniform integer so that they are Cauchy sequence. So there is an integer j such that for j and k greater than or equal to capital J, the distance of fk wi fj wi is less than epsilon over 3. So here we use the condition that we only have finitely many points, the evaluation. Here this for I equal to 1, 2, 3, up to n. That's the purpose of the compactness. Compactness always transform an infinite element to a finite element. Okay, so now let's see. For any z in k, and let wi be the point in D such that the distance between wi minus z is less than delta. This comes from this finite subcover. If k, j are both greater than capital J, we have what? Let's see. The distance between fk, z, fj, z. fk, z, fj, z. We're going to prove that it is a Cauchy sequence. So it's less than or equal to the distance between fk of z and fk of wi, this wi, plus the distance between fk of wi, fj of wi, and plus distance between fj wi, fj of z. Okay, so we just use this wi to form a bridge. So we transform from the kz to kwi and the jwi to jz, and then use the kwi jwi to build the bridge. Okay, this one comes from the equicontinuity. It's less than, and the third one is also equicontinuity, but the middle one comes from this convergence, which is epsilon. All right, so this works for all z in k, so its supremum is going to be less than epsilon. Right? So what we want to prove? We want to prove that the supremum of the distance between fk, fj of z for all z in k is less than epsilon. So here we can get it. So we finish the proof. Finish the proof. Okay. Okay, very good. So that is the complete proof of the Ascoli theorem. Ascoli theorem says if you have a compact set or the compact closure for the for a family f in the CGW is normal. F in the CGW is normal if and only if every point the image fz for all f has a compact closure. It's here. See, you have a normal family if and only if for every point the evaluation has a compact closure and equicontinuity. So the equicontinuity is the essential condition for the Ascoli theorem. So go through this theorem again. In the exam, I may just pick up a small part of the proof and let you to reproduce. Okay, I'm not going to ask you to reproduce the whole complete proof, but maybe in some part I will need you to reproduce the proof. Okay. Okay, so we finished the section 7.1. Finish the section 7.1. It's a long section. It has a lot of informations. So, and so far the materials are very comprehensive and compact. In this section, I don't see the proper exercise, so let's skip this exercise part. When I find some interesting stuff, I will let you know. Okay, so now let's move to the second section. The second section is spaces of analytic functions. Spaces of analytic functions. Okay, so let G be an open subset of C. Let H of G denote the collection of analytic functions defined on G. Of course, this H of G is a subset of a CGC, because we don't have the restriction about the image CGC. And in the textbook, they gave some explanation why we use H of G instead of A of G. What is A of G? A of G is usually the collection of continuous functions from the closure of G to C, which are analytic in G. Okay, so it is continuous to the boundary, analytic inside. So that is A of G. Well, anyway, that's just a tradition. Okay, it's a tradition. When we use A of G, we mean it's analytic inside, continuous up to the boundary. And H is actually so-called holomorphic. Holomorphic functions are analytic functions. They're just a different name. And also there's another name for the analytic function. It's called the regular. It's an important class of functions, so it may have different names from different group of mathematicians. Okay. So anyway, in this textbook, we use H of G, holomorphic functions. A of G means holomorphic, continuous to the boundary. Okay, so when we have a set in a complete metric space, we have a natural constant. Is H of G closed inside CGC? So we want to know the closeness. Okay. Let's see the first theorem. It proved yes, H of G is closed. So if Fn is a sequence in H of G and F belongs to CGC, such that Fn converges to F. Okay, so if you have a convergent sequence to F, then F is analytic, and the kth derivative of Fn will converge to the kth derivative of F for each integer k greater than or equal to 1. So not only the function sequence converges to the limit, the derivative sequence also converges to the derivative of the limit. Okay? Well, let's see how do we prove it. First, let's show F is analytic. F is analytic. We're going to use the Moreira theorem. What is the Moreira theorem? Analytic if and only if over any triangles the integral is always 0. Okay, so let T be a triangle. Contained in G. So T is a triangle contained in G. Of course, T is compact. Here, when we say the triangle, it's over the path. The inside is also inside G. Okay. So you cannot surround some point. So T means the interior part plus a boundary. And the boundary of T is compact. We're going to do the integral. The Fn converges to F, then it converges to F uniformly on T. Okay, whenever you have the uniform continuity, the integral operation is interchangeable with the limit. What I mean is the following. So when you have the integral over T and the limit n approaching infinity Fn, it is equal to the limit n approaching infinity integral Fn along T. And this, the limit of Fn, it is F. And Fn is analytic, so the integral of Fn over T is 0. Limit 0 is 0. So you get the integral of F along T is always equal to 0. So F is analytic in the disk, in a disk containing T, You use a small disk to cover it. And this one, every disk you can find a triangle so that it is the integral is 0. And then this implies F is analytic analytic inside G. Okay, F is going to be analytic inside G. Because analyticity is a local information. Every point you have an open disk, and inside the open disk you apply the Moria theorem. Next, we're going to show the kth derivative of Fn converges to the kth derivative of F. Okay, so first let D be the closed ball centered at A with radius R. It's inside G. Okay, then there is a number capital R greater than little r such that the disk, closed disk, is totally contained in G. All right, so let gamma be the circle Z minus A equal to capital R, the larger one. Then the Cauchy integral formula Cauchy's integral formula gives us remember they are all analytic functions. When we have analytic functions, the kth derivative has a formula, k factorial over 2 pi I integral along gamma Fn of a W minus F of W over W minus Z to power k plus 1 dW. Right? For each Z inside D, inside this disk, smaller one. So we use a larger disk to surround it. Okay? And then we estimate. So by Cauchy's estimate, we have Fk n of Z minus Fk of Z is going to be less than or equal to k factorial over 2 pi. Okay, and here you get the maximum value Mn. Mn is the ups value, the max supremum of Fnw minus F of W, and then you have a 2 pi r, then the denominator you have a r to power k plus 1. All right. No. Let's see this. The denominator is W minus Z to power k plus 1 so far. W minus Z to power k plus 1. But check here. You have A smaller r, the large R, W is here, Z is here. If we want to get the maximum less than case, so we need the smaller distance. The smaller distance, it is greater than capital R minus little r. So when you flip them, it is less than or equal to k factorial 2 pi Mn 2 pi r minus little r ops value to power n plus 1, k plus 1. To power k plus 1. And 2 pi cancelled. And here Mn is the supremum of ops value Fnw minus Fw. W belongs to gamma. W belongs to gamma. Okay? So Fn converges to F. Fn converges to F uniformly along on gamma, because gamma is compact, so it's a uniform convergence. If it's uniform convergence, then the limit of Mn approaching infinity, limit of Fn is going to be 0. Check here, k is the order of the derivative, is constant. R, capital R, little r is constant. Only this Mn depend on the selection of n for different n u capital. So when Mn approaches 0, so the right hand side approaches 0, so this implies, hence it follows that kth derivative of f converges to kth derivative of Fn converges to kth derivative of f uniformly on closed disk centered at A with radius r. So this is a one special closed disk. Let K be an arbitrary compact set. Arbitrary compact subset of G. And we choose this little r so that it is less than the distance between K and the boundary of G. Remember that. And K is compact, so there are finitely many A1, AN in K such that K is covered by the BAJ with radius r, J from 1 to n. So it's open cover has finite subcover situation. So first, for every point, you have this r, and you get this an open disk. Every A you have open disk. Every A you have open disk. So this K is covered by an infinite open cover, and then K is compact. There's a finite subcover. Okay, so you have this. And once you have this one, every point over every disk, it is a uniform convergence. Then over a finitely many disk, it is still uniform convergence. Okay, so kth derivative of Fn converges to kth derivative of f uniformly on K. And this is exactly the proposition we had. The proposition, let me see. Hold on a second. It's exactly the statement in the proposition 1.10. Part B. Proposition 1.10 part B says a sequence Fn in the CG omega with the distance rho converges to f if and only if the sequence Fn converges to f uniformly on all compact subsets of G. So that's why we prove the uniform convergence over every compact subset. If we can prove this, we can say the original sequence converges to the target function f in the distance, in the metric. Okay, so this is a proposition 1.10 part B. It's It's on page 145. 145. Okay, so we finish the proof of the theorem. We get it, the space H of G is closed inside the CG. So H of G is closed inside the CGC. It contains its limit points. It's containing limit point. And because it contains a limit point, once the sequence has a limit, it contains it. Or every Cauchy sequence has its limit. So we have the corollary. We know that the CGC is complete. So the H of G is a complete metric space. Every Cauchy sequence has a limit inside the CGC and is closed, so it's inside H of G. Okay? So once it is complete, remember when we talk about the series, we also use the limit. The series is the limit of the partial sum. Okay? So the corollary in the series language is that if Fn from G to C is analytic and the series Fn of Z n from 1 to infinity converges uniformly on compact sets to f of z. Okay, this condition just means the sequence of the partial sums converges to f of z. Okay, it is just implies that. Then the conclusion is interesting. The conclusion says the case derivative of the limit function is equal to the sigma n from 1 to infinity, the case derivative of Fn of z. So how do we get this corollary? This corollary, let me say something more. So first, we get partial sum Sn of z. Sn of z is j from 1 to n fj of z. And the condition, the series converges uniformly on compact set, just means the sequence Sn of z converges to f of z in CGC or H of G. In CGC or H of G. Okay? And then by the theorem we just proved, we know that the case derivative of Sn converges to the case derivative of f. And the case derivative of Sn, because for the Sn you have you have a finite sum, so it's just partial sum of the case derivative of fj. So that's why when this as a case derivative of Sn of Sz converges to a case derivative of f of z, so this implies, or this is equivalent to the sigma n from 1 to infinity Fn with case derivative of z is equal to case derivative of fz. Okay, so we have term by term differentiation. We have term by term differentiation. Remember that this property only works for the complex analysis. There's no similar theorem for the real variable functions. Okay, so no similar results in the real variable function, real analysis. It is only workable for the complex analysis. The thing is that, remember that we can have absolute value function. Absolute value function, you can use this type of a sequence, a very nice everywhere differentiable function to approximate. So we can use everywhere differentiable real variable function to approximate the absolute value function. But at 0, the absolute value function is not differentiable. So you cannot pass to the derivative at 0. I only say at 0, right? And another example of the theorem mentioned is that we let Fn to be 1 over n x to nth power. Here, the domain is between 0 and 1, and we can see that the limit of Fn n approaches infinity is always 0, because x to nth power is at the most 1 over n approaches infinity. It's equal to 0. This is a uniform convergence. Uniformly. But if we compute the derivative, then we will see that this one does not converge to 0. The derivative 0 is 0, so it does not converge to 0. It's x to n minus 1's power, right? Uniformly. On 0, 1. Of course, at 1, the value is always 1. At any other point, the value is 0. So point-wise limit for x to power n minus 1 is a function g of x equal to 0. If x is between 0 and 1, 1x is 1, it is equal to 1. So it's not even a continuous function. All right, so this is the corollary, and some argument, some remark after the corollary. So in the next video, we are going to study the Hurwitz theorem. The Hurwitz theorem is also an interesting theorem, and we will continue to study the local boundedness and the Montel theorem. Okay, so we finish this video, and we will continue in the next video. Thank you.